let's take a look at what we're doing so far this week. We've been looking at sets and functions. And today, we will be doing cardinality of sets. So I'm excited about this lecture because cardinality is a really nice topic with some really, I think, very nice proofs that I am going to get to explain to you today. So let's get started. What is cardinality, for starters? The cardinality of a set, cardinality of a set A is the number of elements. So it's the size of the set. And it is denoted with sort of absolute value signs, which makes some kind of sense because absolute value is supposed to be like the size of a number, and this is the size of a set. You may also sometimes see it denoted with a little number sign, which also, denotes the number. All right, so let's get some simple examples in here. If we have a set A like this, and let's have a set B like this, so we can do some stuff from a couple lectures ago as well, some unions and intersections. 3, 4, 5. Got two little sets here. So let's see. The cardinality of A is the number of elements. There are 4 elements. We can just count them. So the cardinality of A is 4. Cardinality of B, again, number of elements. That's, in this case, B has 3 elements. And let's do some more. Okay, so what is the cardinality of a union B? Just to bring in some stuff from a couple days ago. So the union means take everything in A and in B and don't count duplicates twice. So count them once. So we get these elements from A and these elements from B, and this thing is the same, so we should only count it once. So let's say that's 6 elements total. And similarly, what is 6? What is the cardinality of A intersect B? Well, what is A intersect B? It's the elements that are contained in both sets. In that case, it's just this guy. So the cardinality of A intersect B is 1. And another thing we did a couple days ago, what is the cardinality of B without A, B minus A? So this is elements of B that are not elements of A. So this one's an element of A, the other 2 are not. So it looks like there's 2 of those. Okay. Oh, why not a couple more? Just to go over everything we did back then. So what's the cardinality of the power set of A? Remember, this is the set of subsets. And I guess there was a practice problem recently, which was if you have a set with n elements, how many elements does the power set have? So maybe some of you have tried this, but if you haven't, I'm going to tell you now. Here's a good way to think about it. Each element can either be in the subset or not in the subset. So you have 2 options. And these are independent, right? Whether 0 is in the subset does not affect whether 1 is in the subset. So there is 2 options for 0, 2 options for 1, and you multiply those to get 4 options total. So the number of elements of the power set is 2 to the power number of elements in your original set. And in this case, that's 2 to the 4, which is 16. And there was another question. If you have two sets A and B, what is the number of elements of A cross B? And remember that A cross B, the Cartesian product, is ordered pairs, something in A, comma, something in B. So it's just all the ways that you can take combinations of these things, which is just multiplying the cardinalities of those two sets. So this should be 4 times 3, which is 12. Okay, so here are some very basic examples. When you're dealing with finite sets with a finite number of elements, then cardinality is pretty simple. But when you're dealing with infinite sets, things get a little bit more complicated. So for example, what is the cardinality of the integers? Well, it's infinity, in some sense, right? It's not a finite number. There are infinitely many elements. And over the course of this lecture, we will try to figure out how to talk about these things in a precise way. So we need to be a little more subtle about this. So let's start by making some definitions that work equally well for finite sets and infinite sets. So if there is an injection from a set A to a set B, then we say that the cardinality of A is less than or equal to the cardinality of B. So remember that an injection, I'm not going to write this down, but remember that an injection means that you don't have any collisions when you go through the map. So every element of A maps to a different element of B. And another way of saying this is that every element of B has at most one preimage. So this is a nice intuitive way of saying that A is at most as big as B, because you can draw, you can write a function that realizes A as looking just like a subset of B, right? You might have extra things here, but at least, this thing is no bigger than this thing. Okay. And similarly, if there is a bijection between A and B, then we say the cardinality of A is equal to the cardinality of B. So again, remember that a bijection means that your map is an injection and a surjection. And another way of saying that is that the elements of A and the elements of B are put in a perfect correspondence. So every one on one side corresponds to a one on the other side. And again, this makes sense to say that these sets are the same size, because this function basically gives you a way of matching them up. For example, you can check, you already know what this means for finite sets, and you can check that taking these definitions does give you what you expect for finite sets. But the point is that this definition, the way we do it this way, works equally well for infinite sets. So we can still talk about these things. If you have an injection, which is to say that the cardinality of A is less than or equal to the cardinality of B, and you have no bijection. So this is saying, let's do some more practice negating quantifiers. This statement is saying that there exists a bijection from A to B. So what's the negation? There does not exist a bijection, so every map between A and B is not a bijection. That's what this means. So, okay, but this is just saying something, hopefully sounds pretty clear. If A is less than or equal to the size of B, and also they have different cardinalities in the sense that there is no bijection, then we say that the cardinality of A is strictly less than the cardinality of B. So a natural question to ask is, can you make this same definition using surjection instead of injection? So if there is a surjection from B to A, can you say this? And the answer is yes. But I will leave that as an exercise. So let's see some examples with infinite sets now. We have a natural injection from the integers to the rational numbers, basically because it's a subset. So this is just sending n to itself, but considered now as a rational number. So what this shows is that the cardinality of the integers is less than or equal to the cardinality of the rational numbers. So we don't know yet whether it's equal or strictly less, but we can say that it is less than or equal to. Redraw that so it doesn't look like a surjection. Cool. Similarly, the rational numbers are a subset of the real numbers, so we have a natural injection there. So the cardinality of the rational numbers is less than or equal to cardinality of the real numbers. And just to give one example where we have a strict inequality so far, if you take some finite set, you can find an injection into the integers. But there is no bijection. So we have an injection, like so, but no bijection. And maybe that's obvious, but if you wanted to be precise about it, you could say something like 0 maps to some integer, 1 also maps to some integer. Take an integer that is bigger than both of those. You know such a thing exists. That is not in the image, so it's not a bijection. So we conclude that the cardinality of 0, 1 is strictly less than the cardinality of the integers, as you would expect.